Welcome to this course on transition metal organometallics in catalysis and biology. We have been discussing about olefin polymerization and in this context we have been talking about olefin classification or polyolefin classification depend from various aspects. For example, from the polymer perspective or from the polymer property point of view, we had spoken about various classifications that exist for polyolefin polymers, namely thermoplastic materials, duraplast, elastomers, elastoplastic materials or thermoplastic elastomers and reversible duraplast. Again, from the polyolefin perspective, we have with regard to polyethylene, we have looked at how many different types they come in, and they come in three varieties, which is LDP, linear low density polyethylene. It can be LLDP, linear low density polyethylene, or HDP, high density polyethylene. So, if polyethylene are graded based on the density of the polymer obtained, and in that there are three varieties. Now, having discussed the polymer classification from polymer perspective or from polymer type point of view, then we moved on to looking at the polymer classification from a chemistry perspective, particularly from the point of view of the process through which they are synthesized, as well as from the point of view of mechanism through which they were synthesized. So, in this category we have spoken for about two types of classification. One is condensation polymer as well as addition polymer. These are from the perspective of the process by which these polymers were synthesized. Similarly, from the mechanism that is followed to produce this polymer, and from this perspective there are two types, which is step growth or the chain growth polymer. So, we have been talking in the last class about the process perspective, which is condensation polymer and addition polymer, and from the mechanism perspective, the two types of polymer are chain growth polymer and step growth polymer. Now, in this context we have studied the condensation polymer in great detail in the previous class, and we saw that many important commercially important polymer like nylon, polyester, polycarbonate polymers are synthesized using this condensation polymer, and these are mainly monomers which are polyfunctionalized, and there can be more than one type, particularly of two type like diamine diacid or diol diacid or diol diacid, diamine diacid, or diol acid chlorides for making this kind of condensation polymer. Now, having discussed the condensation polymer in great detail in the previous lecture, what we are going to be doing today is to look into the other process based polymer, particularly this addition polymer and its example, and followed by the other two classification, that which is classification based on mechanism, that is the chain growth polymer and the step growth polymer. So, having said this, let us now move on to discuss about this addition polymer classification. Now, addition polymers are the ones, or the polymers that are formed from monomers without any loss of a small molecule, unlike the case with condensation polymers. In the condensation polymer, the condensation reaction within the monomer resulted in formation of some small molecule at the byproduct. However, in case of addition polymer, the reaction between monomer does not lead to formation of any byproduct. Addition polymers are formed from monomers without the loss of a small molecule. And the other biggest advantage or characteristics of this addition polymer is that the repeating unit has the same composition as the monomer, whereas in condensation polymer, the repeating unit is not exactly of the same composition as the monomer, because a small molecule has come out of it. So, another important characteristics of addition polymer is that unlike condensation polymers, the repeating unit of an addition polymer has the same composition as the monomer. Okay. So, an example of this kind of polymerization is given below. Mainly the polyethylene polymerization is an example of this addition polymerization, or the vinyl monomers are formed mainly through, are polymerized mainly through this process. NCH2CHY upon polymerization gives CH2CHYN. So, these are vinyl polymerizations using vinyl monomer unit. So, what we see is that polymers can be characterized based on the method in which they are polymerized. One mainly is a condensation method where elimination of small molecule occur, then the other is just an addition method where the small molecule does not occur, and polyvinyl polymers or polyethylene polymers are a result of this addition polymerization. And another important characteristics of this addition polymer is the fact that the composition of the repeat unit of the polymer which is shown over here this is the repeat union of the polymer, this is exactly same as the monomer composition, and that is said over here, repeat union of the addition polymer has the same composition as the monomer. So, this and these two compositions are same. So, now we are going to look at another type of polymer classification, mainly from the mechanistic point of view, and these are the step growth and chain growth mechanism, and this classification is mainly based on the pathway which is used for making these long chain polymers from the monomers. So, let us first start from the step growth polymerization. So, what really distinguish between the step growth and the chain growth is the mechanism by which the step growth polymers are formed. This is illustrated or this is best explained in the definition that follows. Step growth polymerization proceed by a stepwise reaction between functional groups of the reactant. Between the functional group of the reactant shown below. What it means that the polymerization proceeds slowly from monomer to dimer to tetramer, pentamer, so on and so forth. It implies that the polymerization proceeds in multiple steps on going from monomer to dimer to trimer, tetramer, pentamer, and so this can be illustrated below. For example, first monomer will react with another monomer to give dimer, then dimer can react with another monomer to give trimer, dimer can also react with another dimer to give tetramer. Trimer can react with monomer, give tetramer. Trimer can react with dimer to give pentamer. Trimer can react with another trimer, gives hexamer, and this thing proceeds. So, this polymerization proceeds in steps, and as a result of each steps the size of the polymer keeps increasing, like the time as dimer, then trimer, then tetramer, pentamer, hexamer. The size of the polymer keeps increasing, and this can be reflected if one were to measure the polymer molecular weight with the percent conversion for this kind of step growth polymer. So, if one were to look at the molecular weight of the polymer as a function of percent conversion of the monomer. So, this is 0% to 100%, then what is observed over here is that the molecular weight sort of increases, but increases slowly. It is only in the end that there is a sharp increase in molecular weight happen when the longer chain oligomer they react with each other to give even further more longer chain oligomers. So, there is a characteristic trajectory which is known for this kind of step growth polymerization, where the molecular weight increases slowly with converge in the beginning of the reaction, but however, towards the end of the reaction the molecular weight sort of increases drastically as the longer chains react and polymerize to give even longer chain. So, this is a characteristic feature of this kind of step growth polymerization. Now, we are going to look at the other polymerization process, which is called the chain growth polymerization. Now, in chain growth the polymer does not grow like a chain, where each of the chain length gradually grows with each of the monomer are adding to the singular chain, and the chain keeps on increasing. So, this chain growth polymer requires initiator. So, chain growth polymer requires an initiator initiator from which is produced an initiator species R dashed or with a reactive center, and the chain growth takes place like in a chain. The chain growth occurs like in a chain, and this polymerization occurs by propagation of the reactive center by successive addition of large number of monomers in a chain reaction. So, this is sort of explained in this cartoon as is shown here. So, for example, if this is a chain with a reactive propagation center, and to this one monomer comes along, this monomer then gets added to this polymer chain, generating another reactive center, and the species would then be so this monomer would get inserted, and then subsequently another monomer would come and insert. So, the chain has increased by this much in the monomer length, when the second monomer would come and insert this way, and the cycle propagates. It is important to note that these chain growth polymers it is this addition in chain growth polymers growth polymerization addition of large number of molecules of a large number of monomers in a chain reaction chain backbone polymer chain backbone happen fast in a matter of seconds, and a large molecular weight chain polymer chain are formed fast. This also has a trajectory, a polymer molecular weight and percent conversion and what has been found is that the molecular weight is does not change with the percent conversion, because it just forms the equal length polymer no matter what how the reaction proceeds. So, these two graphs, the one in which for the step growth, the other for the chain growth, that sort of as a function of a variation of molecular weight as a function of percent conversion of the monomer tells us insight as to what mechanism is proceeding. Now, there is a third type of polymerization, which is a sort of a living polymerization, and they are mainly seen in biology. Certain polymerization show linear increase of molecular weight with conversion, and so these are sort of living polymerization. And are seen in the biological and are observed in biological synthesis of protein. And for them the characteristics plot of molecular weight versus percent conversion is slightly different. Percent conversion and for this the trajectory which is observed of the molecular weight is something like this, that the molecular weight increases with the percent conversion, and these are mainly seen for biological system or where the polymerization is living. When the monomer comes, the chain further keeps on adding. So, with this we come to the end of today's lecture, which was primarily polymer classification from a chemistry perspective, particularly from a process perspective, where we discussed about this condensation polymer and the addition polymer with examples. Then we also looked at how the mechanistic classification about polymerization would vary, and in this from mechanistic classification we have seen that the polymers can be classified into two types. One is the step growth as well as the chain growth, and for each of these step growth and chain growth we have discussed their characteristic molecular weight versus percent conversion curves. In step growth polymerization, there is a sudden increase in higher molecular weight towards the end of the conversion, and sort of the exponential the curve sort of stays gently increases in the beginning of the conversion, whereas towards the end it rises sharply. Whereas for the chain growth, what we saw that the molecular weight is kind of fixed and does not change with percent conversion. And lastly, we had spoken about biological processes where certain polymerization show increase molecular weight with percent conversion, and these are sort of polymerization which are living in nature and they are seen in biology, particularly with regard to protein synthesis. So, with this I conclude today's discussion on chain polymer classification, and we are going to be discussing more on this olefin polymerization as we meet next. Till then, goodbye and thank you.
you.